Hi friends, I am Dr. V.V. Hussain, belongs to Arts, Commerce and Science College RV. Friends, today in this video lecture we are going to discuss the derivation of phase rule. In 1874, Willard Gibbs have discovered a relationship governing all heterogeneous equilibria. The relationship is F is equal to C minus P plus 2, where F is number of degrees of freedom, C is the number of components, P the number of phases. Now this rule states that the number of degrees of freedom is always exceed the difference between the number of component and the number of phases by 2. Or if we write this relationship like this, P plus F is equal to C plus 2. We just transpose this P in this side. So how can we state the phase rule? That the sum of the number of phases and the number of degrees of freedom always exceed the number of component by 2, provided that the equilibrium should not be disturbed by electrical field, magnetic field or any other chemical force. Now let us try to derive this relationship. For this purpose, we have to consider a general heterogeneous system having P number of phases, that is alpha, beta, gamma, delta, P up to P phases, and in each phase C number of components, namely C1, C2, C3, C. So the total number of components are C, which are distributed among these phases. Now, the number of degrees of freedom, F, can also be given as the total number of variables minus the total number of independent equations. So let us try to calculate the total number of variables. Now variables, the thermodynamic variables, that is temperature, pressure, volume and compositions. Now we write this temperature, pressure, volume and composition. These are the variables we can consider in a thermochemical systems or our chemical heterogeneous systems. Out of the temperature, pressure and volume, we can can select only two. Why? Here, pressure, temperature and volume are related by equation PV is equal to nRT. You know that the ideal gas equation. Here, if we have two variables, third one gets automatically fixed by the equation PV is equal to nRT. So out of these variables, PPV variables, we select only two. So there are two variables can be selected out of temperature and pressure. Friends, now there is a question of composition. You see that, let us consider that in the alpha phase there are only two components, C1 and C2. In order to express the concentration of component out of the two components, we will have to know the concentration of one component. For example, among here, suppose C1 is 10%. So automatically C2 is 90%. If we select three components, C1, C2 and C3 here, we will have to know the concentration of two components so that you can express the concentration of all components. Here suppose C1 is 10%, C2 is 20%, then automatically C3 will be 70%. Now we have in this alpha phase or one phase C components. So we require for a phase C minus 1 concentration terms. So the total concentration terms for one phase will be equal to C into C minus 1. Now friends, we have how many phases? P phases. So for total of P phases, we will have how many concentration terms? P into C minus 1 terms. Now we have the total number of variables. One temperature, second pressure and P into C minus 1 concentration terms. So the total number of variables that's equal to P into C minus 1 plus 2. Say equation number 1. Now let us calculate the total number of independent equations. Now let us concentrate on a C1 component, the first component. Here the C1 is in equilibrium, that means C1 in alpha phase is in equilibrium with C1 in beta phase, which is in equilibrium with C1 in gamma phase and so on. Let us consider that our heterogeneous system have only three phases, alpha, beta, gamma and one component C1. Now for equilibrium, we know that the chemical potential mu is always constant. So we can write chemical potential of the first component, that is C1, in alpha phase is equal to the chemical potential of the same component in beta phase, which is equal to chemical potential of the first component in gamma phase. Now in this relationship, you will have two equality signs. So here we will have two independent equations. Actually there are three equations are there. Let me write mu1 alpha, that's equal to mu1 beta. Mu1 beta, that's equal to mu1 gamma. Third can be written as mu1 alpha, that can be equal to mu1 gamma. Now here in these equations, two equations are independent. Out of these three equations, you can have only two independent equations. One becomes dependent. So we will have to select only two dependent equations. Now here we have selected three phases, that is alpha, beta and gamma. For three phases you get two independent equations for a component 1. So for the same component for p phases, you will have for p phases considering C1 component, how many independent equations? That is p minus 1 independent equations. Or you will have the, if you write this equation for p phases, then you will have p minus 1 equality signs. Okay. Now for C components, for one component you will have p minus 1 independent equation. So for C number of component, as C into p minus 1 independent equations. Now we know that what is the number of degrees of freedom? Yes, F is equal to total number of variables minus total number of independent equations. Now let's put the value. Here total number of variables are P into C minus 1 plus 2 minus total number of independent equations C into P minus 1. If you solve it, you will get PC minus P plus 2 minus CP plus C. So this cancels out. So what you get? C minus P plus 2. Or P plus F is equal to C plus 2. The equation is known as